Dear colleagues, my name is Švec and this is my colleague Roderik Ploszek. We are from Institute of Computer Science and Mathematics from Slovak University of Technology, and today we would like to present you our work entitled Review of Encryption Schemes Used in Modern Ransomware. So firstly, we are going to start with introduction to the ransomware. Then we describe our analysis process. Next, we describe the well-known encryption schemes used in ransomware and take a closer look to the schemes that we observed in the latest samples. Then we will describe the specific encryption algorithms, key generation functions, and implementation details used in older ransomware and compare them to the current samples. And lastly, we will summarize our findings and also talk about the possible future of ransomware. Ransomware can be defined as a special type of malware that encrypts all the user data, such as photos or documents, and does not provide a decryption key unless a ransom is paid. Attackers usually often prefer payments through Bitcoin. When the encryption is finished, the ransomware usually provides instruction how to pay ransom, either by changing a desktop background or putting a README file in every directory which contains encrypted files. According to 2019 Internet Organized Crime Threat Assessment, the ransomware is still reported as a top threat. And also modern ransomware attacks are shifting focus towards more valuable targets, such as private companies instead of individual users. And while targeting specific companies is more technically challenging, the attackers can set the ransom based on the victim's ability to pay, and there were even cases where companies' encrypted files have been ransomed for over 1 million euros. Our main research objective was to analyze current ransomware samples detected during 2019 and early 2020. We specifically focused on encryption schemes, that is, what kind of algorithms are used, where the keys are generated and stored, how the keys are actually generated, and lastly, how the encryption algorithms are implemented. Our goal was to understand the current trends in ransomware and compare the findings with the previous generation samples. All the presented samples were manually analyzed. We obtained a set of samples from public malware archives and used combination of static and dynamic analysis using standard tools such as IDA, Ghidra, or OliDebugger. Analysis of a single sample proved to be a very complicated task, since almost all the samples used some form of anti-reverse engineering techniques such as packers, code obfuscation, or statically linked libraries. Generally, there are 4 well-known encryption schemes used by ransomware in recent years. In the first scheme, the ransomware is shipped with a public key, which is used for symmetric key encryption, and symmetric key is generated for each file to be encrypted. Second scheme, on the other hand, generates public and private key pair on the victim side. In this scheme, the private key needs to be sent back to the attacker and removed from victim's computer, and file encryption works similar to the first scheme. In the third scheme comes again with the hard-coded public key used for global symmetric key encryption, and this time one key is used for all files. Last scheme, known as a 3-tier trust model, uses 2 public and private key pairs, where the shipped public key from key pair A is used to encrypt another random generated private key from key pair B, and public key B is then used for encrypting the symmetric keys, similarly to the previous schemes. This scheme was ultimately used by the famous WannaCry ransomware and can be considered as the most secure one, as the users affected by the same binary cannot share the private keys because they are protected by another layer. During our research, we find out that the most recent samples uses first and second scheme. So here you can see the encryption scheme that was used by a lot of samples, such as Ryuk or Logbit. The attacker generates a specific public and private key pair for a victim and embeds the public key directly into the malicious executable. When the sample is run on the victim machine, for each file that the ransomware encrypts, it generates a unique symmetric key, which is used for data encryption. Then this key is encrypted with the victim public key and attached at the end of an encrypted file, usually with the additional values that the encryption algorithm may need, like initialization vector or nonce. At first glance, it may look like a vulnerable scheme because if multiple victims are infected with the same executable, it is possible to pay the ransom once and decrypt many machines with the received private key. However, many studies have shown, as I mentioned earlier, that the modern ransomware is focusing on specific targets instead of infecting as many machines as possible. So the attackers are preparing custom binaries, each with a unique key. Second encryption scheme that we encountered during our research takes a slightly different approach, and it is more suitable for mass infection campaigns. This time, the executable comes with a special attacker's key. When the sample is run, the public and private key pair is generated directly on the victim machine. Then a private key is encrypted with the embedded key and sent back to the attacker. When the message is sent, the encrypted key is removed from the memory. The file encryption process is again similar to the previous scheme, where unique symmetric key is used for each file and encrypted with the freshly generated public key. This scheme has one weakness, and that is if the victim has logs from the network traffic, which is rather unusual for regular users. It is trivial to decrypt all files since the encrypted private key is transmitted to the attacker and it is encrypted with a known key. This scheme was observed, for example, in the Gantt-Crab ransomware. So the next part will be presented by my colleague.
Thank you, Peter. In the following slides, we will compare analysis of older ransomware analyzed in previous research with our findings analyzing ransomware that's more modern. We will start with symmetric ciphers. Just by looking at the table, you can already see a few insecure ciphers, such as RC4 in the Open2U ransomware and a custom cipher in XMass ransomware. Other ciphers used, such as AES, Blowfish, and Salsa20, are secure. However, ransomware GlobeV3, although using AES 256, used in secure electronic codebook mode. Moving on, these are the samples that we've analyzed so far. You can see that AES 128 is dominating with 3 samples, and there's one sample of AES 256. We haven't encountered any incorrect block cipher mode, just that Ryuk uses 0 IV padding, which is not ideal, but it doesn't make the cipher less secure. There were also lesser known ciphers, such as Area 128 in Lilocked ransomware, and that's a Korean cipher. There was also one special case of a custom cipher in Klopp ransomware, which I'll talk about later. Now let's take a look at asymmetric ciphers used in older ransomware. Everything looks fine with elliptic curves and RSA with a secure key length. There's one specialty. The GP code ransomware uses 660-bit key. This might be because it was a recommended length in the 90s and authors probably read about it in an older publication or a manual. In the samples we've analyzed, we have encountered just the RSA algorithm. 4 samples used 2048-bit key and 2 samples used 1024-bit key. Let's take a look at the key generation in older ransomware. You can see a typical mistake of using a rand function from the C standard library, which reduces the key space and makes brute force attack possible. A ransomware Petya was using a standard elliptic curve, and ransomwares Open2U and La Chiffre had the keys hard-coded in the binary. Now for our findings. Unlike previous researchers, we've separately determined key generation for symmetric algorithms and asymmetric algorithms. Symmetric keys were generated using functions from the cryptographic APIs, so the cryptographic randomness should not be a problem here. Asymmetric keys were mostly hard-coded, or as in the case of SamSam, passed as an argument from the ransomware loader. Potential victim may not be connected to the internet, and for the attacker it is safer to use a pre-generated asymmetric key pair. A Gantt grab is an exception to this, since the key is sent to the attacker. Previous research didn't go as far as to actually determine the implementations of cryptographic functions, so we cannot compare our findings to older generations of ransomware. But you can see that the standard Windows crypto API is dominant. By the way, Microsoft no longer recommends using this API because they've got a newer next generation crypto API that should be used by new projects. There are also a few specialties. SamSam as a .NET ransomware uses .NET cryptographic functions. Ransomware Dharma uses AX TLS embedded SSL library for its cryptographic functions. And Lockbit, in addition to Windows Crypto API, uses fast instructions for AES if they are present on the CPU, and otherwise it uses its own optimized version of AES. Now let me tell you about a custom algorithm we've encountered. This is from the Club ransomware. It uses a cipher state that's a permutation of bytes from 0 to 255. There's no repetition. It looks like on the slide. The initial permutation is given by a random 117-byte key. That's almost 940 bits of key space. Now the encryption works for every byte of the input file. 2 bytes from the cipher state are exchanged, and these 2 bytes are used to compute the final index of a cipher state that's actually XORed to the original file byte. And that continues for each byte of the input file. Note that contents of the file have no impact on the state of the cipher. As a final comparison, we've seen that authors in the past were using insecure random generators like RAND from C standard library, ECB, modes, and custom ciphers. From our findings, in the newest versions and samples of ransomware, there's prevalence of correct implementations, and mistakes or custom ciphers are less common. For the end of our presentation, let's talk about the future of cryptography for ransomware. I don't know if this is distant future or if it's around the corner, but quantum computers are getting better and the number of qubits is increasing. With this, we can see classic algorithms such as RSA be prone to quantum factorization attacks. And if authors of ransomware will keep following trends, we will certainly see ransomware that's using post-quantum algorithms in the future. In conclusion, we still continue analyzing more samples, and we want to expand our database of analyzed samples. Informations we have extracted can be used, for example, in detection systems. For example, at our institute, we have a group of researchers focused on detection of malware using ontologies. Thank you for your attention. Hopefully, we'll be able to answer your questions during the Zoom call, and you can also contact us at email addresses shown on the screen. Thanks again.